Okay, this question is about a white solid, MHCO3, that dissolves in water and then reacts with hydrochloric acid to give us salt. So we've got this reacting with that, so these two are reacting in a 1:1 ratio. The student was asked to design an experiment to determine the value for the MR of this. So the MR is going to be equal to mass divided by the number of moles. That's just for later. The student dissolved 1464 milligrams. So that here is 1.464 grams. In water, made it up to 250 centimetres cubed. Let me draw a little picture here. So that's the MHCO3, and we've got 1.464 grams of that. It's made up to 250 centimetres cubed, and 10 centimetres cubed of this was taken out. Sorry, 25 centimetres cubed of this was taken out, so that's a tenth. So going that way is a tenth. So if I go back the other way, I need to times it by 10. Again, just sitting here working it out as I go. And then this was titrated with hydrochloric acid, which we know is 1:1. And the concentration of that is 0.102. So I've got my titration results table here. Calculate the mean titer and use this to determine the amount in moles of HCl. So I never use the rough. So out of the three that I've got available now, I'm looking for the two closest, which is these two here. So I need to do the mean of those. So I add them together, divide it by 2. So the mean titer is 9.75 plus 9.65 divided by 2, which gives you 9.7 centimetres cubed, or 9.70 centimetres cubed. So the number of moles then of hydrochloric acid, so I'm just working this bit out here. So how many moles of hydrochloric acid has reacted with 25 centimetres cubed of my solution of MHCO3? That is equal to concentration times volume. The concentration is 0.102 and the volume is 9.7. And remember, I need to divide that by 1,000. So that equals, that gives me 9.89. 9.89 times 10 to the minus 4 moles. Okay, so I've worked out the number of moles of this bit here. So part B, calculate the moles of MHCO3 in the 250 centimetres cubed solution. So my hydrochloric acid reacts with MHCO3 in a 1:1 ratio. So I'll start with the number of moles of MHCO3 in 25 centimetres cubed is the same, 9.89 times 10 to the minus 4. So to go back to 250 centimetres cubed, I need to times that by 10. So 9.89. Don't know what happened there, but I'll carry on from here. So number of moles in 250 equals 9.89 times 10 to the minus 4 times 10. That equals 9.89 times 10 to the minus 3. That's moles of MHCO3. Now, that is in my 250 centimetres cubed. So that was in my big flask at the start, of which I've got my mass. So my MR then is equal to the mass, 1.464, divided by the number of moles, which I've got here, 9.89 times 10 to the minus 3, which equals 148 grams per mole. Okay, so there's my answer there. So the marks for this, in 1A there's 1 mark for selecting the 2 correct titers, 1 mark for calculating the mean titer correctly, and 1 mark for calculating the number of moles. In part B there's 1 mark for multiplying by 10 to get the number of moles in 250 centimetres cubed. 1 mark for using the correct mass, 1.464 grams, sorry, 1.464 grams, and then one mark for calculating the MR correctly, 148. Now the student identify the burette as the largest source of uncertainty. So let's just draw that. So there's the burette. Here's the flask that it was going into, and this has the biggest source of error. And if you look at the mean titers in a burette, we're using 9.7 centimetres cubed in a burette that will deliver 50 centimetres cubed. So your error here is going to be quite large because remember the error is the measurement. So if burettes read to kind of 0.1, so 0.1 divided by 9.7 times 100. The only way that I can kind of make that percentage error smaller is by increasing this. If I increase the number on the bottom, then what I end up doing is reducing the overall value, the value of the percentage error that I would work out over here. And there's 2 ways I can do that. So basically what I need here is I need to add more volume of HCl. So 2 ways that I can do that. Number 1, I could use hydrochloric acid that is more dilute, because obviously then I would use a greater volume to neutralise the MHCO3. Or I could use a larger amount of MHCO3, because if there's a larger amount of MHCO3 in here, again, I'm going to require a larger volume of hydrochloric acid in order to react with that. So I'll do them both. So I can use dilute or more dilute HCl. So that's one suggestion that I could use. And the justification then is a larger titer or a larger volume would be used. And alternatively, what I could have had is use a larger mass of MHCO3, and again it's the same thing. So a larger mass of MHCO3 also means that a larger titer of HCl would be required in order to neutralise that. Part D, another student is required to make up 250 centimetres cubed of an aqueous solution that contains a known mass of MHCO3. The student is provided with a sample bottle containing MHCO3. Describe the method, including apparatus and practical details that the student should use to prepare a solution. So this is a couple of things here. This is a levelled response. It's quite a common levelled response, making up a standard solution. And like when you've done these a few times, you'll get this. So the kind of 3 stages really here is the first stage is weighing and transferring the mass. So this is all about the mass. The second stage, which I'll put down here, is then dissolving it in water. And then the third stage, which I'm slightly out of room. Yeah, I'm out of room, but I can certainly squash that in or move things up as I need. The third one here is transferring, washing, and kind of mixing / it says agitation in the mark scheme, but it's kind of making sure that it's all mixed together. So transfer, washing, and agitation, which is basically mixing. So let's start at the beginning. So in order to do the mass, now remember when we measure masses, we always do it by by difference. So we need to describe how we're going to do that. So the first thing we would do is weigh sample bottle. Okay, I'll do it as some bullet points, but I'll need to do it in a row if I'm going to fit all this on. So weigh a sample bottle. Weigh a sample bottle with sample. That's the first point. So tip sample into beaker. And reweigh the sample bottle. Okay, so what you would do then is record the difference. And of course the reason we do that is because sometimes a little bit will be left in the sample bottle or the sample tube. Okay, so that's the main way that we would do that. So in terms of the dissolving, this is all in a beaker, remember, because we've added it into a beaker, and that's what we do to do the dissolving. Okay, so now if we're making it up to 250 centimetres cubed, the water that we use for the dissolving has got to be less than that. So I'd say add 100 centimetres cubed of distilled water. And stir until all dissolved. Okay, and then the third and final one here. So this is now getting it from the beaker, and I'll start this one up here. Okay, so this is getting from the beaker to the volumetric flask. So transfer to volumetric flask. And again, remember, as you tip it in, there's going to be a bit of solution left over. So with the washings. So we wash, and this is why we only use 100 centimetres cubed of water, because any bits of water that we use to wash from the beaker into the flask, obviously that's going to take it closer to 250, but obviously, we're not going to go over the mark. So we transfer the solution that's in the beaker into the flask, and then we wash the beaker into the flask as well. Now we need to make it up to 250 centimetres cubed. So add distilled water to 250 centimetres cubed. Okay, and then this mixing part here, and this is the one that is often forgotten here, and then shake or invert to mix thoroughly. And that is it, that's that one done.